Good morning, all. Today, we analyze the constraint motions. We are familiar with constraints. It is some limitations or some restrictions given to the system in motion. Here we consider three examples. The first one is a wedge and a block. Let us consider this figure. From the figure, it is clear that in an inclined plane, that is inclined at an angle theta, a mass is placed. We know that the mass may or may not move. It depends on mass of the block, angle of wedge, and something about the property of the wedge. So here we take that the surface is plane and it is smooth. By smooth, we means there is no friction force. That is, we neglect friction. And we know that when we solving a physical system using Newtonian mechanics, there are several steps. The first step was to isolate the masses and then to draw the force diagram, then the equation of motion, next the constraint equations. In these examples, we are going to analyze only the constraint equations. Here we do not take the complete steps. Here we carry out only the fourth step, that is to obtain the constraint equations. From the figure, the angle of the wedge is taken as h. The angle of wedge is taken as theta, and This angle makes an height h here. The angle of wedge is theta, and this height is the maximum height of the wedge is h, and the height to the mass is taken as y. Okay. Here our aim is to relate the accelerations of the block and the wedge. Here, an important thing to be noted is that here the wedge is also moving. The wedge is moving in x direction, and the mass is sliding on that wedge. So there must be two motions, one of the wedge and the other of the block. So our aim is to relate the acceleration of the block and the acceleration of the wedge. Here we consider the motion until the mass take off from the wedge. Okay, and here also we assume that the mass is in contact with the wedge. Throughout the analysis, throughout our analysis, the block is stay on the wedged plane. Okay. As there is no vertical moment for the wedge, the vertical acceleration of the wedge is 0. Here the wedge is moving on. Here the wedge is moving in this direction, this x direction. Okay, and there is no movement along y direction. Okay, so we can say that the vertical acceleration of the wedge is 0. And here the constraint is the angle of the wedge is a constant, or the slope is a constant. Throughout the motion, the slope of the wedge is a constant, and we assumed that the wedge sorry the block slides on the wedge and the angle of the wedge is constant. So the constraint here is this one, that is the slope is a constant. Here it is the constraint. Constraint is a limitation or restriction. So here this is the constraint, that is slope is a constant. So we have to express the slope in terms of the parameters of the wedge and block. From mathematics, you will heard about the slope, isn't it? What is slope? How can we represent the slope using x and y coordinates in a planar motion? Okay, the slope is given by y by x, or it is some angle. This depend on some angles, or we can express it as the slope is equal to tan theta, isn't it? Here, if we consider an xy plane, it is y axis and it is x axis. Okay, then if we have a line that is starting from here and this is our line, then the angle made by the line with x axis is taken as theta. Then if we consider this length as x and this length as y, then tan theta must be equal to y by x. It is the slope. If y increases, what will happen? If y increases, for the same value of x, if y increases, the angle will increase. Then the slope must increase. Okay. Then we can write slope, that is tan theta, and here in this case it is y by x. And now we analyze our problem. Okay, and here in our problem we know that the angle of the wedge is theta, and here in this figure this is our block, let it be mass m, and here if this angle is theta, this angle must be theta. If we draw a parallel about the this lower edge of the block, then this angle must be theta. Okay, and this height is h, and the distance to the mass, to the block from the lower edge of the wedge is y. Then this marked side must be equal to h minus y, and also this distance, that must be equal to small x minus capital X. Small x is the distance to the mass in the x direction, and capital X is the distance to the wedge in x direction. Then it is x minus x. From this one, from the lower figure, we have to take the slope, then it is equal to, what is the expression for slope? Slope must be equal to tan theta. Okay, then tan theta is equal to h minus y divided by x minus x. We cross multiplying this, we multiply x minus x with tan theta and 1 with, and here we write tan theta by 1, then 1 with h minus y. Then we express h minus y is equal to x minus x tan theta. Okay. If we consider only the motion in x direction, x is the positions of block and wedge respectively, then x double dot means second order derivative with respect to time, isn't it? That is d square x divided by dt square. To obtain x double dot, to obtain small x double dot or capital X double dot, what we have to do? We have to find the time derivative 2 times. We have to differentiate 2 times with respect to time. Okay, then we know that h is a constant. Okay, and here y is a changing quantity, x is changing quantity, and theta also a constant. Okay, then here we find the derivative. Okay, 2 times. Then when we find the derivative of h minus y, x minus x tan theta, what is the result? As h is a constant, we will get minus y dot is equal to x dot minus capital X dot into tan theta. Here, as tan theta is constant, we differentiate x and small x and capital X. Then this is the quantity. Then we find the derivative once more. Then minus y double dot is equal to small x double dot minus capital X double dot into tan theta. Then we can write y double dot is equal to we have to multiply a minus here. Then this capital X double dot must be positive. So capital X double dot minus small x double dot into tan theta. So after differentiation, we will get the result as y double dot is equal to x double dot minus small x double dot into tan theta. Okay, here what is y? Y is the vertical position of the block and x is the horizontal position of the block and capital X is the horizontal position of wedge. Then y double dot is acceleration, vertical acceleration, and x double dot is the horizontal acceleration of the block and x double dot is the horizontal acceleration of the wedge. Then this is the connection relating the accelerations of wedge and block. Now we go to another example, that is masses and pulley. Consider the figure. Here a pulley having a radius r, it is free to rotate about this axis, about an axis through its center. Its radius is capital R and a string having a particular length and two masses 1 and 2 is tightened at the both ends of the string and it is kept on the pulley. And in the figure we have marked A, capital A, it is the acceleration of the pulley. Here also we assume that the total system, the pulley with these masses moving upward and also due to the two masses hanging on the pulley, they may move up or down according to their masses. So here we want to analyze the accelerations of that masses, here also we use the constraint equations. So here we consider two masses m1 and m2 are connected by a string that passes over a pulley, and the pulley is accelerating upward at an acceleration capital A as shown, and the gravitational force is acting downwards. Acceleration, the gravitation force is, so there must be acceleration g downwards. Okay, and here we assume that there is no horizontal motion. Okay, here we only consider the vertical motions. The pulley is moving upward with an acceleration a, capital A, and the masses m1 and m2 may move down or up according to their weights or according to their masses. Here our aim is to find how the accelerations of the two bodies are related. Here also we consider the constraint. Here what will be the constraint? Here we use an inextensible string. That is, the length of the string is a constant. The length of the string is a constant. Let it be small l. Then we have to write an expression for length of the string in terms of the other parameters. Look at the figure. A is the acceleration and r is the radius of the pulley, and here xp is the, here the distance xp, it is the distance from ground to the center of pulley, and y1 is the vertical distance to the mass 1 and y2 is the vertical distance to mass 2. Here we can represent it is not by xp, let it be yp. Yp is the let it be yp. Okay, then yp is the vertical distance to the center of pulley, and y1 is the height to the first mass, and y2 is the height to the second mass. Then here what will be the length? Look at the figure. Here, from here, the string starts. This is string and it is passed over the pulley up to here, and this is up to the second mass. Okay, then we have to divide it by some length. First is this length. Okay, this is the first length, and this is the second up to this one. It is a semicircle. Okay, from here point to this point, and the third distance is this one. Okay, then the length 1, the total length of the string is 1 length 1 plus length 2 to 2 plus length 3. If we add the 3 length, it must be the length of the string. So what will be this distance? Marked as 1. What is the distance? Marked 1. Look at here, it is yp and it is y1. Then it must be equal to the 1 first distance, that must be equal to yp minus y1. And the second distance, what is the second distance? It is the half of the circumference of the circle radius r. We know that the circumference of a circle having radius r is 2 pi r. Then half of that must be pi r. Then the second is pi r. And the third is this length. It is here, this is yp and this is y2. Then we can write it as yp minus y2. Then the total length, then the total length L must be equal to, look at here, L must be equal to pi r plus yp minus y1 plus yp minus y2. Here there is a yp plus and there is another yp here. Then we have to sum it. Then we arrange the expression as here we can simply arrange the expression as pi r plus 2yp plus here there is a minus y1, there is a minus y2. Then we can write with the negative sign y1 plus y2. Okay, here only the radius r is a constant. Okay, and L is also a constant. Then differentiating this equation twice with respect to time, what is the result? When we differentiating this one time, 0 must be equal to 0 plus 2yp dot minus y1 dot minus y2 dot, isn't it? Okay, differentiating once more, we will get, I write a 0 here and not taking this 0, it is also is equal to 0. Then I write 2yp double dot minus y1 double dot minus y2 double dot. Here we assume that the acceleration of the pulley upward is yp. Here this acceleration is capital A, or here it is yp double dash is A. Then from this expression it is 2A minus y1 double dash minus y2 double dash, or that is equal to 0. From this expression we can express what is A. What will be A? A must be equal to, from here we can obtain 2A is equal to what? y1 double dash plus y2 double dash, or A must be equal to y1 double dash plus y2 double dash divided by 2. Okay. And this is the connection, that is the acceleration of the pulley is connected with the accelerations of the two masses. Okay. Then we move to the next example. In the next example, there is pulley system. There is a mass and two pulleys. Here also this pulley is used to lift this block. Okay. Using such a system, our effort can be reduced. Have you used the pulley in your home? Is it familiar to you? Okay. We use such pulleys to take water from open wells. Okay. Here our aim is to relate the acceleration of the end of the rope to the acceleration of the block. Okay. Here also take the length as constraint. As the string is an inextensible, we can express this length up to this point, length up to this point. Okay. Here we use the two pulleys with radius r. Okay. Then this is the x distance. The distance is x, and here from this one to this point the distance must be equal to pi r. And what will be this distance from this point to this point? What is this? This is x Okay, this distance is x and this distance is h. Then this distance must be equal to capital X. It is capital X. This is capital X minus h. Okay, and here this is small x, and this quantity, this is also is equal to pi r, and this is pi r. Then from this point to this point, it must be equal to small x minus h. Okay, then look at the sum. L is equal to x plus pi r plus x minus h plus pi r plus x minus h. Okay, so differentiating this two times. Here we know that this is constant, pi r is a constant, and here also pi r is a constant, and this h is small h is also a constant because this height is fixed, but capital X is not fixed and small x is not fixed. Okay, then when we differentiating this in first point, we get, taking the first order derivative, we will get this is equal to, this is equal to x double dot plus x, sorry, x dot plus x dot. Here it is x dot, and here also then it is plus, here it is x dot, here it is x dot, capital X dot, and here is small x dot. Then 2x double, sorry, 2x dot is equal to minus x dot. Then capital X double dot also is equal to 2x double dot is equal to minus x dot, or x double dot is equal to minus 1 by 2 x double dot, minus 1 by 2 x double dot. Okay, so we will get 2x double dot plus x double dot. So x double dot is equal to minus x double dot by 2. It means that the block accelerate half as fast, and it is in the opposite direction. Okay, so the block accelerate half as fast, but it is in opposite direction. That is the block moving upward, and we moving our hand downwards. This is the last example in the constraint motion. Here we only analyzed the constraint equation, and from that we obtain some properties about the motion in the system. Okay, so I stop here. Thank you.